Here's my question. We're going to review what is a random variable. So I'm usually going to write RV for random variable. So what is a random variable? Well, you learn the definition in your probability class, and then you sort of forget the definition because you don't really use it much. You just think of, well, it's a number with a probability, just as an unknown number with a probability distribution. That's sort of the intuitive way of thinking about it. And you tend to forget, and that answers most questions, that most of your homework problems. You tend to forget the original definition that you were given. So who remembers the original definition?
It's a function that maps from sample space to state space.
Yes, exactly. So, well, I would say, yeah, in particular, I would say the reals. People use different terms for different things. I would say random element would be that would be the generic term I use, but for random variable, I usually think of mapping to the reals. All right, so yes, it's a function. It's well, there's this extra little term. It's a measurable function. It's a measurable function from the sample space. Whoops. Omega to R. All right, so it's a measurable. Don't worry about measurable. People make a big deal about this. I tend to think that it's actually, this question of measurability is not usually relevant. Some people would have a fit if they heard me say that, but I've got my reasons. All right, so let's just, it's just a function from a sample space. A sample space is a set with a probability with, as some of its subsets have probabilities assigned to them, and those are called events. And if you take a function from a sample space to the reals, it's called a random variable. All right, so let's let x and y be random variables on a sample space. All right, and let's consider the linear combination ax plus by. All right, so what type of object is ax plus by? Is it also a random variable? Yeah, it's another random variable. So you've got this set of objects that you can take linear combinations of and get another object in the set. What does that remind you of? I guess the fact that I was talking about linear algebra. Yes, it reminds you of a vector space. All right, you take linear combinations of your items in a set, and you get another item in the set. Well, that's how vector spaces work. Okay, I'm jumping the gun a little bit. So just to make sure you're clear, this ax plus by, it's the function that maps each omega in omega to, well, a times whatever x maps omega to, plus b times whatever y maps omega to. And it's also measurable. This is something that you would have to, it also has the property of being well behaved enough to be called a random variable. And again, I don't want to make a big deal about that. So it's another random variable. All right, and we've said, okay, we're taking linear combinations of these things and getting other random variables. Well, the set of random variables, that intuition leads you to this idea that the set of random variables is a vector space. Now, okay, just because you can take linear combinations and you get another one, that's not entirely everything that you would need to establish that it's a vector space, but the other things are very simple. You can check. I'm not going to bother. You can check other vec space properties, defining properties. All right, so it's a vector space. You take linear combinations and you get another random variable. All right, here's an interesting subspace of the vector space of random variables. Consider any constant C. Any constant C can be treated, especially if you were doing like C plus X. What would that mean? Well, if C is a random, we're trying to add random variables. What would C plus X, does the addition have to be countable? Well, that's beyond the scope of the course, but it's a good question, but it's beyond the scope of the course. I'm going to refer you to the name of what we're doing. I'll give it away, is L2. You can look up L2 theory, and there is a lot of complicated questions that have to be dealt with very carefully. So rather than trying to, let's see. Also, I don't remember off the top of my head. I'll have to think about it. That's the main reason I'm deflecting, but there are going to be a lot of complicated questions that you can have to think about. I don't think countable. I don't think it's guaranteed that that countable sums work, countable linear combinations work. All right, any constant C what was I saying? Can be treated as the, let's say, I'll put random in quotation marks, as the random variable that maps every omega in omega to C. All right, so you have a constant. If you want to add a random variable to a constant, well, that can be thought of as just an ordinary vector space of random variables operation. And you just sort of think of C as the function. C is the function that maps everything in omega to the number C. All right, and it's just some real number. So if you need to treat a constant as a random variable, that's fine. There is a random variable that behaves like you would want that constant to behave. That behaves like a constant. It maps everything in omega to the same number. All right. Okay, well, here's another interesting subspace. Okay, well, I didn't say that this is a subspace. So if you take any two constants, take a linear combination of them, you get another constant. So that's a subspace, right? That's the set of constants is a subspace of the set of the vector space of random variables. So the set of constants, you take a linear combination, you get another constant. You can treat them, you can think of them as random variables, special subset of the random variables, and you take a linear combination of constants, you get another constant. So the set of constants is a subspace. And in particular, every constant is proportional to the constant 1. So it's what's the dimension of this subspace? All right. Let's see, I'm sure I've got a bunch of 1s in here, yes. All right, it's a one-dimensional subspace. All right, the set of random variables is a vector space. The set of constants is a subspace of that vector space. All right, here's another important subspace. Let's see, if X and Y have finite variance, then so does the linear combination ax plus by. All right, so what does that tell us? That tells us that, and this is an assertion, I'm not gonna, there's a formula that you can use to verify this, but let's just take this on faith for now if you don't remember the formula. So the set of random variables with finite variance is a subspace. All right, you take a linear combination of random variables with finite variance, you get another random variable with finite variance. So that's a subspace of this vector space of all random variables. When I say all random variables, I mean all random variables defined on a particular sample space. So this is always, it's not every conceivable random variable ever. It's, you have a sample space in mind, and the set of all random variables are really what I mean, are the set of all random variables mapping from that sample space to the reals. Just to clarify. All right, and we're going to jump right to the main point of this. The main benefit of thinking about random variables as vectors in a vector space. Well, once you zero in on the subspace of random variables with finite variance, this vector space, or this subspace, the random variables with finite variance, it has a dot product. It has a dot product, all right? Defined by, okay, I have two random variables, x, and I want to dot, and I'm thinking of them as vectors, right? This random variable is a vector, this random variable is a vector, and I'm dotting them together. What do I mean by that? Well, in in linear algebra, you multiplied their coordinates together and then took the sum of those products. Here, we're doing something a little bit different. I mean, it turns out that this operation is equivalent in some sense, but that's a very advanced result. It turns out that if you take any two random variables and you calculate their expected product, this expected product behaves almost exactly the same as a dot product does in familiar Euclidean linear algebra. There's a preferred notation that rather than doing x dot y, today I'll probably use a little bit of both, but really the preferred notation for taking the dot product of vectors x and y is xy. Okay, and people will stick a little L2 at the bottom. That's the name that's given to the vector space of all random variables with finite variance. L2. And really the preferred term would be inner product rather than dot product. But to me, that's not an important distinction. So I'm just gonna say dot product, but I might put it in quotation marks, sorry. So there is a notion of dot product. Well, that gives you a notion of orthogonality, gives you a notion of angles in general, and it just sort of imparts a geometry to the space of random variables. There are geometric ways of thinking about random variables and their relationships to each other. And when I came to understand this, it was a big breakthrough for me, and it really resonated. And that's really why I'm delivering this. I want to impart this to those of you who are like me, who are visual learners, who this idea will really resonate with. this isn't going to be crucial to the course on the whole. I would like to use it a few times, and we're going to get some good results out of thinking in this way and drawing some pictures that are along these lines. But this is an advanced way of thinking, and it is challenging. So, all right, maybe it'll seem less challenging once I start drawing some pictures and giving some examples here in a second. But it's just, maybe it seems more challenging than it is. It's just, you just think of, well, I've got a vector space. Instead of vectors in R3, I've got vectors that really are random variables. And if I want to take the dot product and see if two random variables are orthogonal, for example, well, instead of having coordinates to take products of and add up the products, I just need to calculate the expected product of the random variables. And if this is 0, for example, then these random variables are orthogonal in the vector space of vectors with finite variance. All right. Well, there's one more aspect to this. We don't just have a dot product. We have a corresponding norm and a corresponding, well, I'll define the squared norm defined by, and this shouldn't actually look, this is nothing new. If you think about how we defined the dot product, the squared norm is supposed to be, all right, I'll draw a little L2 over here. The squared norm of a vector is supposed to be its dot product with itself. So what would that look like if the dot product is defined to be the expected product of the two vectors? Well, if it's x dot x, then it's just expectation of x times x. So this is a squared norm. This is the length of x. Squared length of x is just its expected square. All right, and then just, I've said this, but these behave in many ways like the familiar Euclidean dot product and norm. All right, it's going to be easier once we start drawing pictures and thinking about examples. All right, so what's an example? All right, here's an example of what you might do. So I've said, we've got orthogonality here, a potential for thinking about orthogonality. So you actually also have orthogonal projection. So here's an example. Find the orthogonal projection of x. Let me move this up. All right. Onto the subspace of constants. All right, we talked about the idea of treating constants as random variables, and actually every constant, does it have a finite expected squared distance from itself, or from its average? Well, yes, its variance is 0. Every constant has variance 0. So so the subspace of constants is also, it's not just a subspace of the random variables, it's also a subspace of the random variables with finite variance. All right, so assume x has finite variance. All right, maybe I'll add that just to make sure we're perfectly clear. finite variance. Find the orthogonal projection of x onto the subspace of constants. Well, in other words, find, I'm gonna say x hat in R such that, all right, well, maybe I'll draw the picture and then I'll finish talking about the condition. Okay, so here's a picture. Let's see. I'm gonna draw. All right, this is the subspace. This one-dimensional line represents the subspace of constants. All right, and let me draw another vector. Oh, that shouldn't be curved. Let me try to do that a little bit better. It's not much better. All right, and here's x. All right, x is a vector. The subspace of constants is the subspace. And I'm drawing a little picture that includes both of these vectors. Maybe I want to extend the, all right. I'm drawing a picture that includes the subspace of constants and the vector x. And I'm gonna claim that's a legitimate picture. All right, this is well, these are vectors in L2. And what's the dimension of L2? Well, who knows? It depends on omega. It can be infinite. But I'm drawing a picture that has the vector x and the subspace of constants, and I'm going to see if this drawing can give me some intuition regarding this question I've posed, finding an orthogonal projection of x onto the subspace of constants. And maybe it'll give intuition for more than just that after we figured that out. All right, so these are vectors in L2, so I've got a little two-dimensional picture. So is this a legitimate picture? Have I accurately depicted a two-dimensional subspace of R2? I mean L2 of the set of vectors with finite variance. Well, how many dimensions do I need to make a drawing that includes the vector x and the subspace of constants? How many dimensions would that span?
I mean, you could just make x one of the basis vectors and like one the other, so it could be two.
Yeah. Well, okay, that's true. So I could just define a basis for it that, well, it wouldn't necessarily be an orthonormal basis. So I wouldn't necessarily want to imagine them as the axes. But let's just say, so you're not thinking about these as the axes. You're thinking about these as basis vectors. All right, have it one and x are a basis for a two-dimensional subspace. I think that's what you're getting at. And yes, the span of 1 and x is two-dimensional. And really, as long as I've got the one vector, I've got the whole subspace of constants. So this two-dimensional depiction really is capturing, I should say x could be a constant, in which case really you're only one-dimensional, but that doesn't really detract from the legitimacy of a two-dimensional picture. All right, so I've got two vectors of interest in L2. I don't know the dimension of L2, and I don't care necessarily because the span of these two vectors is a two-dimensional subspace of L2, and there's no problem in drawing it. There's nothing. I'm not going to mislead myself by drawing a two-dimensional picture that includes x and the subspace of constants, because there is a two-dimensional subspace of L2 that includes x and the constants. Now, this is going to help us think more clearly about this question of an orthogonal projection. What does an orthogonal projection look like? We need to kind of come down from X and hit this subspace in such a way that we make a right angle, right? All right, if we do that, then the place where I land, that's X hat, and I'm trying to use a lowercase x hat here. This is supposed to be a capital X and a lowercase x hat. All right, so there's some constant where if I drop down from X, I hit the subspace of constants orthogonally. What constant is this? Where do I land? All right, and so I mean, just the linear algebra definition would be X minus X hat, right? That's this difference here. X minus X hat is supposed to be orthogonal to every constant. Their dot product, so now I'm using this other fancy notation. Their dot product should be equal to 0 for every constant. For every constant, the dot product of this residual vector, X minus X hat, with that constant vector should be 0. All right, well, how did I define this L2 dot product? It's the expected product. Expectation, X minus X hat with C equals 0. Well, C is a constant, and actually C doesn't matter. I can divide both sides by C. And I really just need expectation X minus X hat to be 0. I can take the expectation, I can distribute the expectation X minus expectation X hat. Well, any constant is expectation is just itself. So let me just, expectation X minus expectation X hat is just X hat equals 0. I add X hat to both sides and I get X hat equals expectation X. So actually I can go ahead and erase this and say, I know where I land. I land exactly at expectation X. All right, so that's kind of interesting. Let me write that as a neat little fact, and then we're about to use that fact to get another neat fact. So the orthogonal projection of X onto the subspace of constants is just the expectation, right? That's a constant. Expectation of X is a constant, and that's where you land when you hit this subspace orthogonally. You land at your expectation. All right, now I'm gonna. Okay, so I mean that doesn't really tell you anything interesting necessarily on its own. It's kind of interesting to see the picture, but now we're gonna figure out something that follows easily from this. I mean, assuming you have to take on faith that this expected product does behave like a dot product and works like in familiar ways. But if you'll still believe me, I'm going to add another point to the picture, and let's call it, well, let's just say C. Here's some arbitrary C. You know what? Let me call it A because I've been using C in this derivation. All right, so here's some other constant, A. Now I'm going to draw that line, okay? And I've got a little triangle here. I know how to relate the lengths of the sides of this triangle because it is a right triangle, right? If I pick any A, constant A, I can draw a right triangle that includes X and the expectation of X and the constant A. I've got a right triangle that includes these sides or these vertices. What happens if we apply the Pythagorean theorem to this right triangle? What happens if we apply the Pythagorean theorem? We have the squared length of the hypotenuse. And oh, maybe I should write it over here so we don't have to move our. All right, don't have to scroll up and down. Our Pythagorean theorem. By Pythagorean theorem, the squared length of x minus a, this vector minus that vector, all right, that's the length of this side, squared length. And remember these you know, the notion of norm that I've and dot product, right, these sort of have special definitions for random variables. So this squared length equals this squared length plus this squared length. Well, maybe I'll write this one first. The squared length of expectation x minus a plus the squared length of x minus expectation x. So this is just the Pythagorean theorem applied to this vector space of random variables with finite variance. And I've got x and a constant a, and if I draw this picture, I realize that I can decompose this squared length into the sum of these two squared lengths because of orthogonality and right triangle properties. But what does this mean in a more familiar notation? All right, so what does this really, how would I write this without all this L2 stuff? This, you know, this is still very confusing notation to you all. So, all right, so let's translate this back into familiar notation. What does this mean in familiar notation? The norm really just means the expected square. All right. So I'll just go ahead and write that each time. All right, let's see if let me see what's in the chat here. Oh, dot colon equal means I'm defining something. So it's not, I mean, I'm not too careful in distinguishing necessarily, but usually colon equal means you're defining something rather than sort of stating it as a fact that could be derived, for example. Is defined to be, you can say it is defined to be equal to. All right, so what does this look like? Now this is actually an interesting statement. It's a really interesting statement. First of all, expectation x is a constant, and so is a. So really this expectation is superfluous. So I'm going to erase it. And what is this? What is this term? This term has a name. Anyone recognize the expected square of x minus its expectation? Variance. This is the variance of x. And this is just the square difference between the expectation of x and a. So the expected square difference between x and any constant decomposes into, well, just the variance of x plus the how far x is on average from a squared. So this is a term that doesn't depend on a, and this is a term that only depends on the distribution of x via its expectation. That's a really interesting fact. Actually, it's got a name. It's called the bias-variance decomposition. And this isn't the only way to derive the bias-variance decomposition. It can be derived very readily without drawing this nice picture. But Well, when you've got the picture, you've also got, you don't just have the fact, you have sort of an extra potential for extra meaning behind this fact. And, being able to think about it visually and intuitively and, maybe understand why it works and how it can be extended and how, variations on it would work. All right, this is called the bias-variance decomposition. And, well, why is it called the bias-variance decomposition? Well, actually, first of all, let me ask a question. So, which A and R, which real number has the smallest expected square distance from X? So I want you to look at this. I actually want you to take, I want everyone to just look at this equation, the bias-variance decomposition, and say, on the left, expected different distance between X and A squared. I'm trying to minimize this. What constant would minimize this? Well, if you look on the right, you find that you decomposed it in such a way that one of the terms doesn't have anything to do with A. So really, all you need to do is figure out which A minimizes this term. So which A is that? Right. So we've got some good answers here. Well, this term can only be 0. The smallest this term can be is 0, and it will only be 0 if A is equal to the expectation of X. Anything else, this term is non-zero, and you've got an expected square distance that's larger than it would have been if A was expectation X. So this is just, one application of the bias-variance decomposition. It just immediately tells you how to minimize the expected square distance from X. What constant has the smallest expected square distance from X? It's just the expectation. And you see that by inspecting the terms that you get from the bias-variance decomposition. So, well, why is it called the bias-variance decomposition? Well, for estimation, I mean, you've probably seen this, but well, for estimation, you have your random variable is your estimator and your constant is your truth. All right, so let's say theta hat minus theta. Expected square distance between your estimator and the truth. So this is the truth is a constant, and your estimator depends on the data. So it's a random. I'll just say it's random. And this decomposes into, well, let me write it in the same order that I've written it up here. The expectation of theta hat minus theta squared plus the variance of theta hat, the random variable. And this has a name of squared bias of theta hat for theta. All right, let me see how we're doing on time. All right, I think we're fine. I'm just gonna show sort of one more thing that I think is interesting about this picture. I'll do one more picture. One more picture, and then again, we're not gonna, I know this is advanced, and so if you need to take some time to make sense of it, then don't feel bad. But we're gonna do one more picture, and I mean, largely what we're gonna do is we're just gonna sort of get some facts out of thinking in this way. And I do hope that you can make sense of this well enough to, maybe do some straightforward questions along these lines, at least in the homework, maybe on the quiz or test, but I'm not going to guarantee that. I'll get some feedback first about just how challenging this is. I mean, really, a lot of times all you really need to do is you start out with some quantity or some familiar type of quantity, and you rewrite it as in terms of vector operations like norms or dot products, and then you apply a familiar vector operation to that, like the Pythagorean theorem, and then you go back and rewrite the result in terms of more familiar random variable quantities like expectations. And I mean, that's sort of a pathway. Really, that's what that's one way of going from expectation x minus a squared equals squared bias plus variance. I start here, say, well, I want to try to decompose this, or I want to try to work, see if there's anything interesting I can say about the expected square difference between x and a. I recognize it as a norm of a vector, x minus a squared norm, I should say. I apply the Pythagorean theorem to rewrite that squared norm as a sum of these two squared norms, and then I can go back and rewrite each of those in the more familiar random variable expectation notations, and that completes the derivation and provides me with something that it wouldn't have been obvious without making reference to the vector space way of thinking. So I think you'll have one homework question like this, probably the first homework, and I'm going to outline it like almost exactly. So don't worry. I'm going to outline the steps, and it'll be as about as straightforward as possible. By the way, you'll get the homework. I would think today. I may not have all of the problems posted, and I think the first homework will be due a week from Sunday, and it'll be a little bit longer than most, probably because it's a longer. Usually, it's going to be a weekly assignment. This one will be a little bit longer than most, probably because it's more like 2 weeks worth of material. All right, but anyway, more of the logistics will come in just a second. So let's just do one more little thing. So it's useful if you're trying to make use of this vector space stuff. It's useful to sort of recognize that some familiar quantity has a vector, has a neat vector space representation. So vector representations of familiar quantities. We've already one of them, so we'll review it and we'll see one more. And the one that we've seen is variance. We saw that there's a neat representation of variance, vector representations of familiar quantities. So I just want to add covariance to that list. All right, the covariance of two random variables, x and y, is defined to be, well, implicitly, when you write covariance, you're thinking these have finite variance. All right, expectation x minus ex, y minus ey, right? That's the definition. How would I write this as a dot product between vectors? Expected product of these two random variables is exactly, well, I guess it's hard to say and it's hard to type, so I'll just write it. That is the dot product between these two random variables thought of as vectors. All right, so this is just the covariance between x and y is the dot product between, so maybe we'll give a term, the centered version of x and the centered version of y. And you can see this in the picture. This is an important, this is an important actual vector. Let's see. Let me make it maybe orange. All right. This is an important vector. All right. X minus, that is, maybe I need to zoom in. All right, that's the trick. This is the centered version of X. It's just the deviation X minus EX. All right, that's as good as I'm going to get it. And I didn't do the double bar for the expectation. Okay. X minus EX. That's its deviation from the subspace of constants. And if you have X and Y, and you are thinking about their covariance, well, that is the dot product between their centered versions. What about the variance of X? Well, it's the expected square of X minus EX. So it's the expected square of the centered version of X. And in terms of our vector space quantities, we defined that expected square, that was defined to be the norm. That was the norm for this vector space of random variables with finite variance.
Professor,
So,
sorry to interrupt.
yeah.
When you wrote the covariance as a dot product, should it have been X minus expected X, not expected Y?
Thank you. Yes, thank you very much. Good catch. Yep. All right, thank you for clarifying. So when you do see something like that, I'm not great at keeping up with the chat. So I do appreciate just unmuting and stopping me instead of relying on me to catch a comment in the chat. So thank you very much. All right. So here's an intuitive interpretation of the variance of a random variable. It is, well, how far that vector is from the constants. Well, the square, or you could say the square distance of X from the subspace of constants. That's its variance. The further it is from the constants, the larger variance it has. And really, those are, that's just, you can say those are equivalent ways of thinking about variance. How far does X tend to be from its expectation? That's the familiar way of thinking about variance with the usual sort of notation. But if you're thinking about random variables as vectors in a vector space, the variance of X is how far it is. Well, you could say the standard deviation is how far it is from the subspace of constants, and its variance is its squared distance from the subspace of constants. I think that's quite a nice intuition.